Then we start with the event. Okay. Hello, everyone. Welcome to the second event of the Energy, Sustainability, and Circularity Seminar Series, organized by the Department of Chemical Engineering, University of Liège. My name is Motiar Rahman, and I'm an assistant professor at the Department of Chemical Engineering and the coordinator of this seminar series. The main idea behind organizing this seminar series is to listen to the world leaders and experts on a range of topics related to energy and sustainability. It's a pleasure to welcome Professor Klaus Lackner as our speaker today. Professor Lackner is the founding director of the Center for Negative Carbon Emissions and a professor in the School of Sustainable Engineering and the Built Environment at Arizona State University, USA. He obtained his PhD in theoretical physics with the highest honor summa cum laude from Heidelberg University, Germany in 1978. Prior to his academic positions, he held appointments at the theoretical division of Los Alamos National Laboratory, USA for nearly 19 years. He was the director of the Lenfest Center for Sustainable Energy at the Earth Institute and professor in the Environmental Engineering Department at Columbia University, USA from 2001 to 2014. He joined the Arizona State University as a professor in 2014. He also co-founded one of the first private air capture companies, Global Research Technologies, in Arizona. Professor Lackner designed the prototype mechanical tree, which was on display at the Our Future Planet exhibition at the Science Museum, London from 2021 to 2022. He's a pioneer in carbon management, and in 1999, Professor Lackner was the first person to suggest the technical capture of carbon dioxide from the air in the context of carbon management. Without further delay, I would now like to invite Professor Lackner to take the stage. Thank you.
Well, thank you so much. Thank you for having me. And today, I think I was getting overly ambitious and tried to give you a big overview over a systems approach to balancing the carbon budget. Of course, direct air capture will play a prominent role in this, but it is not entirely focused on that topic. I hope I get through in the allotted time, but I will give it a try. So ultimately, I would like to make a clear distinction about how we address the climate problem, and in the context I have been working on it since the early 90s. And I think it's really a question whether we focus on carbon or whether we focus on climate. And I would argue that isolating excess carbon as it enters the environment is a very specific problem, which deserves its own focus. And of course, it is directly related to the climate change problem. It's not the only one. There are other greenhouse gases. And so the focus for us is to look at the carbon budget. And I would argue that if you look at it historically and look at where the big players are, balancing the carbon budget largely fixes climate and ocean acidification. It doesn't do it entirely, but I would argue if you solve that part of the problem, you are 90% of the way there. And if you try to solve the other parts, well, then mainly you have left the problem alone. And I would argue one of the reasons this is so important is that carbon accounting is far simpler than greenhouse gas accounting. It already starts with a simple question: what's the conversion factor between methane and carbon dioxide? And it is much simpler to say we're keeping track of carbon as it is extracted from the ground, and we keep track of carbon as it is being put back away in sequestration, typically back into the ground. So if you do that, the extraction of fossil carbon from the ground, including, by the way, the CO2, which comes out with natural gas, or in occasions in pure streams, needs to be accounted on the one side of the ledger. On the same side of the ledger, you also will find CO2 that's generated from the calcination of limestone and dolomite. That happens mainly in the cemented steel production. And then you could take that carbon sequestration from point sources and from the environment and close the loop that way. Ultimately, carbon capture and storage must be safe and permanent. And one caveat in all of this, of course, from the start is that this is waste management. You can really think of it like that. We extracted carbon from the ground. We don't know what to do with it. We don't really care about it. We wanted the energy. And now we have to dispose of the waste CO2. This is waste management on an unprecedented scale. If you look at it in terms of current emissions, that's about 40 gigatons per year. And it's likely to stay that way. People are talking about that it gradually goes down. But if you look at energy consumption growing at roughly 2% a year over decades, by the end of the century, we are roughly 5 times as large as we are right now in our energy consumption. And if we manage to squeeze out 80% of the carbon, well, then we are still 40 gigatons a year because we just multiplied by 5 and divided by 5. On the other side, if we are in an overshoot world, and I would strongly argue we already are, we may be just entering that, but I do think we have a very hard time stopping CO2 piling up to less than 500 ppm. And at some point in the foreseeable future, in the next few decades, we will probably decide that too much is too much and that we need to get 100 ppm back out of the atmosphere. And that roughly translates into 40 gigatons of CO2 for 40 years. So either way, this is a fantastically large scale, which needs to be looked at. Now, carbon management, I would argue, or carbon waste management, if you like, is technically feasible. There's no question about it. People have demonstrated it. There are many different options, and I would argue it's unlikely that a single one will take over. They have today different degrees of maturity. They differ in the scale they can reach and the cost they currently have and are likely to have in the future. There are clearly biomass options. I would argue, as a rule, their cost is low, which makes it interesting. You can start there. Sometimes it's medium. If you get into fancy biochar operations, things can get quite expensive too. Their scalability, I would argue, is poor to medium. I have like to point out, if you simply think of photosynthesis as collecting carbon, you now have a coupling to the sunshine, you know roughly the efficiency of conversion, and you can convince yourself quite easily that it will take more agricultural land, more land than we currently have in agriculture to actually get to that 40 gigatons. So the bottom line is, I think biomass options will help us get started. They will never be large enough to make it work. Of course, we can collect CO2 from point sources and then store that carbon. I would argue the cost now is medium to high. The scalability of this is medium. You can get very large, particularly you can get larger as our energy infrastructure gets larger. But I think it's worth keeping in mind it's inherently limited to substantially less than current emissions, or the emissions you have at that moment, I should say more carefully. It's complicated further complicated by the introduction of intermittent renewable energy, which really doesn't make it easier, because if you want to grab the CO2 from a power plant, the capital investments don't look so good if you have to deal with a power plant which only runs at peak times. I would argue historically we have looked at this, and I think generally retrofits typically fail. And the reason is quite obvious. Getting all that CO2 is a big change in the system design, and it's actually too difficult to re-optimize an old coal plant that was designed around the fact that coal is cheap. And now if I'd pay for the CO2, the effective price of the coal is very high. So then the last option you have is carbon dioxide removal, or carbon removal more generally, which is often known as CDR, by technical means. So here we are talking about direct air capture. We are talking about those kind of things. Here, the scalability is excellent. You can go to basically any scale you like, and you can convince yourself quite easily that direct air capture or extracting CO2 from the ocean does not run into limits until it reaches the full scale of what it needs to do. On the other hand, the cost of this is horrible. So we have to get order of magnitude lower costs before that actually is viable. If you look at these technologies, there are a number of them available. They have a wide range of environmental footprints and carbon accountability. If you look at ocean alkalinity, the accounting is quite complex. The duration of how long that excess alkalinity actually stays in the ocean can be debated. Some people argue it will take tens of thousands of years. Others argue that all the ocean will flow through a coral reef, the surface ocean, in the next few hundred years. And there's no guarantee that corals couldn't reset the alkalinity to where they want it to be. And it has an unknown, potentially large environmental footprint. If you go to accelerated weathering in soils, that certainly can collect CO2 and can store it, presumably quite for long times. Accounting is now very difficult because you basically have to believe that it does what you think it does, and that it didn't flow away and got out of your ability to make contact with the atmosphere. And it potentially has a very large environmental footprint because you are basically spreading over agricultural fields what other people would call mine tailings. Then you can go to ocean carbon capture with geological or mineral storage. I think here the accounting is quite straightforward because you have the CO2 in hand after you did all of that. Of course, you don't have the indirect emissions, but quite frankly, they apply to all of these things. What the indirect emissions, which you get out of life cycle analysis, are very complicated and are very hard to get accurately accounted for. And the same is true for direct air capture, again, coupled with geological or mineral storage. The accounting is simple, again, except for the indirect emissions. But overall, I would argue those two can scale, but both of them are expensive. And right now, I would argue direct air capture is ahead of the game. And I think for a simple reason. In the ocean, I need to pick through 25,000 or 26,000 water molecules before I find a carbon molecule. And in the air, it's only 1 in 2,500. Yes, it's denser in the ocean, but the ocean, because the ocean is 1,000 times denser than the air, the ocean water. But on the other hand, it is more diluted because there's more water. So ultimately, if we want to look at all of this and try to close the carbon cycle, I would view the way of getting my hands on the carbon as one aspect of the problem, which is a typical industrial problem with all the complications and all the rules which go with that. The harder part of the problem, in my view, is how do you store that carbon safely and permanently on long timescales. The relevant timescales, I would argue, and there's a societal issue here I'll come back to in a second, the relevant timescales are ultimately determined by climate science. You really want to know, if I let that carbon out into the environment, how long will it take to naturally go away? And it turns out, unfortunately, that's a very long time constant. If you care just about the climate, you could make the case that the ocean will buffer most of it, but not all of it, over the next 1,000 years or so. But if you look at natural mineralization processes, which gradually will pull the excess carbon back out, you're talking about tens of thousands of years. And this is not something that is debatable. This has been known in the geosciences for decades. There's nothing new about that. So if we disturb the system, we are disturbing it for tens of thousands of years. So the time constant in which you need to talk storage have to be on that order. On the other hand, the responsibility for doing that ultimately depends on policy. If societies say we don't care about it, then we will not deal with it. Right? On the other hand, if the polluter has to pay and the intergenerational equity is upheld, then storage operators must guarantee that sequestration lasts on those climate relevant timescales. That guarantee may involve a promise to restore lost carbon that allows you to consider temporary storage, but that then requires a chain of liability. And I would argue that looking at it up front, you cannot really exceed that liability chain of for much more than institutional timescales. And we can argue what those are. but I would argue we have historically had a very hard time to guarantee things, write contracts which are expected to be binding, which last much more than 100 years. So I would argue there's a clear break in this thing where you say short times I can deal with institutional guarantees, insurances, operator liability, you name it. But if you go past 100 years, you better have a scientific guarantee that this is actually safe. Of course, as I said before, societies could abdicate this responsibility. And I would argue de facto that we have one now. Because if you look at storage discussions, carbon credits, hardly any give you guarantees which go past 100 years. And many of them actually only go 30 years. Stefania Arkusa and I we are looking at it, and she analyzed what Microsoft had done. And basically, after 30 years, roughly half of the carbon that has been removed and been paid for in a credit has been orphaned. In other words, it may still be in the ground, it may still be stored, but nobody is liable in case it isn't. So if storage is fit for purpose, you have to satisfy certain requirements. We just talked about permanent on a climate time scale. It doesn't mean billions of years, but it means tens of thousands of years. In other words, I can't think, and we're just writing a paper around this topic, the expected losses should be smaller than the expected natural removal of carbon. Right? So, and you can do the prorate that if you are 1% of the stored carbon, then you cannot be more than 1% of the natural removal of carbon. Of course, storage has to be safe. It has to be safe today for people who live nearby, and it has to be safe for future generations. There should be no sudden losses. It shouldn't cause seismic activities. It shouldn't ruin groundwater, you name it. There should be a minimal environmental footprint. So some things you can say, well, this mobilizes heavy metals, or it is a severe change in ecosystems. All of those things you would like to avoid. I think there has to be a well-defined liability for carbon losses on the institutional timescales. You could do this with storage operator liability or public guarantees. And you need a well-established scientific understanding of long-term durability, right? That introduces, by the way, the risk that over the next 100 years, there's a change in scientific understanding, and we do have to make a reason for that, an adjustment for that. In that case, I would argue that carbon is lost, and I'm particularly suspicious of carbon storage technologies that promise 500 years, because I do not know how to continue after 500 years. But if you look at it, there are solutions which are short-term. There are solutions that are long-term. I would argue most geological storage fits that bill. Most mineralization fits that bill. But technical CDR is definitely stuck on costs right now. Cost reductions, and I'll discuss this a little more in a minute, need to be on the order of about an order of magnitude. If we don't get 10 times cheaper, then fixing the climate problem could bankrupt the world, or alternatively render climate damages unmanageable. And of course, that could then also bankrupt the world, right? The strategy in many ways, in my view, has to be learning by doing. We can do a lot of science around it, we can debate it, and we can make it a little better here and there, but ultimately we need to just do it, and then things tend to get cheaper. Think of wind, think of solar, think of lots of other technologies, from washing machines to your computer. There's plenty of precedents, but there's no guarantee that it always works. Nuclear power, for example, didn't work out like that. And of course, learning by doing requires demand for all that doing. And if that demand doesn't materialize, then we have a problem. And I think that's where we are right now. We can't move forward because nobody wants to pay for it. And nobody really wants to pay for it until climate change really hurts. Right? So it demands regulations or volunteers. And I think at the end of the day, governments can provide both, although there's a clear indication that some private companies are entering into this, like I just mentioned, Microsoft. But ultimately, it cannot be done without political will. And I would summarize that as saying waste management is never free, but typically it's worth the effort, that otherwise we wouldn't do it. We do it for sewage, and nobody argues. We do it for municipal waste, and nobody argues. And we just need to get over that hurdle and accept that CO2 needs to be cleaned up too. So I have a proposal, or Stephanie and Arkansas and I are pursuing a proposal for a regulatory approach. We are strongly supportive of the carbon take-back obligation, and we think of it as an extended manufacturer's liability. We argue the obvious place to take care of this problem is all the way up front, because we now look at carbon rather than at greenhouse gases. You mobilize carbon by extracting fossil fuels, and at that point you pay or you perform the certified removal of carbon. Carbon is balanced at the source if you do that, and that has some implications, right? One is every carbon that is now in the environment is actually already properly balanced out and therefore can be used to clean up again. Storage operators are liable for the stored carbon, we argue. If lost accidentally or because it was by design temporary, the operator needs to purchase a new certificate to make the old certificate whole again, right? Basically, you can make it work that way. This allows for temporary storage within institutional timescales. We would argue 500-year storage cannot be certified because I cannot give a guarantee that in 500 years from now we clean it up again. Long-term storage then has to be certified through scientific consensus. You can say mineralization, we know for thermodynamic grounds, is not likely to change, and the probability that you lose it over the next 10,000 years is indeed extremely small. All carbon that is extracted then is immediately cleared by carbon removal. So the world is in balance then by definition, and there is no need to track carbon through the economy. That's actually important because I do believe that life cycle assessments lack accounting level accuracy, but of course are useful for engineering. You want to know whether you made an improvement or not. But if you do it this way, and you, for example, do direct air capture and find that your life cycle assessment lacks, that you actually emit more indirectly than you directly remove, you would go bankrupt because you can generate one certificate of sequestration, but implicit in your supply chain, you paid for 2 or 3. So clearly that doesn't work, and I don't have to prove to you that that doesn't work economically. You just can't make it work. And in this case, then also all mobile carbon is equivalent, and all mobile carbon may be sequestered. Right? The distinction between point source capture and CDR in a world which has gone that way is actually no longer necessary. So in my view, reducing the cost of carbon removal is that ultimate chicken and egg problem, right? Cost won't come down without regulations, and regulations won't be introduced until costs are low. So we do need in the beginning volunteers and niche markets where you can actually try things out and make it work. So here we have another proposal which we are trying to move forward and get on the table, and it's not all that easy. We say we should differentiate from the start between legacy emissions, stuff which happened in the past, and continued emissions. And we build up negative emissions to remove legacy emissions as a public effort. That allows you to learn. That is sort of the voluntary side, and institutions and companies could help with that, right? You drive costs down through learning by doing for everyone, including industry, which will need it, right? In the process, you pay back the public carbon debt. So take an extreme version of it, say we remove 200 years of emissions over 50 years. That means every first year, we don't have to be all that good because we remove 1800 to 1804. There weren't all that many emissions. As we climb up that curve, we are then 4 times faster than in real time, and in 50 years from now, we would have caught up, right? If we were to do something like that, we would get the learning necessary. But then I would hold extractive industries responsible as soon as it's politically feasible. And future extractions, unless balanced by removal, create a carbon debt. And I'm perfectly happy to say this debt cannot be paid right now because we don't have the wherewithal. But just like a financial debt, like going to the bank, it's a real debt and you can't weasel out of it. And it's a well-defined payback schedule by which you have to do that, which then requires another institutional agreement. How do you actually do that? But you then have guaranteed futures of removing carbon. But you really should think of carbon coming out of the ground as scope one. We always do scope one and scope zero, right? We always talk about 1, 2, and 3, but the problem is somebody's scope one is somebody else's scope two and somebody else's scope three, and we can endlessly discuss who is responsible. But if you simply tie the responsibility right at the moment it comes out of the ground, which we refer to as scope zero, then scope 1, 2, and 3 sort of become irrelevant. It's already taken care of, right? In a way, in that scenario, fossil fuel companies must act, but the rest of society is ending up paying the extra cost. The benefit to the rest of the society is that they now have a climate that is manageable. And the help to industry, I would argue, should be limited to the cost reductions which come from having developed the technology. You know, the quid pro quo ultimately is that legacy emissions are a public debt, which would undoubtedly bankrupt all the private companies who incurred it over the last 200 years. So ultimately, that also frees other industries and sectors of society from carbon responsibility. I can see how Microsoft can keep track of its carbon. I don't see how a little restaurant or bakery could possibly balance out its carbon because it simply doesn't have the wherewithal to know how much it actually emitted. And so therefore, having done it that way, that problem has simply evaporated. Let me go to an entirely different point in this talk, where I'm pointing out now that the energy transition will proceed even without the threat of climate change. And I would argue this has happened in the last few years because intermittent photovoltaic electric energy is now cheaper than chemical energy and natural gas, and in some places cheaper than chemical energy and coal. I added this last sentence because I'm giving this talk now in Europe. In the US, it's not true. Coal is still cheaper. The chemical energy in coal is still cheaper than the kilowatt hours coming out of a solar panel. But for natural gas, even with the cheap natural gas in the US, this is no longer true. And I would point out the conversion of coal is miserably difficult because it's so dirty. And even in the US, the electric power generation from cheap natural gas completely outcompetes even cheap coal. So therefore, in a way, we suddenly have that intermittent photovoltaic energy as a raw energy source, not as consumer electricity, beating everything else in the market. And that will have enormous repercussions where things go. And if you want to have a hint of what might happen, look at fracking in the US. In 1995, people didn't know that it's even possible. There's a nice paper by Rogner et al., which as a footnote says, of course we know about all these shales, but nobody has any idea how to tap into them. In 2005, it tipped, and it was cheaper than natural gas from any other source. And by 2015, it dominated the market in the US. And I think photovoltaic power has the same potential. And it will just wedge itself into the market because it can, because it's cheaper than everything else. And ultimately, these economics will drive where things go. The problem, of course, it's highly intermittent and it needs a complement, right? And things fall apart on the second level. In a way, it's not just photovoltaic power, it's also the demand. The combination of photovoltaic power and demand, both of them are inflexible in many ways, and they don't match, right? You have mismatches on the second level that leads to grid instabilities. You have it on the minutes, on hours. Clouds come over, days you have weather fluctuations. They can last for weeks, and seasonality then kicks in. And ultimately, I would argue even interannual variability is significant. A colleague of mine looked at wind speeds at airports, and sunshine is even worse, by the way, and over decades. And there are vast differences from year to year. So if you rely on a technology like this, we need storage at all of these time scales. And the storage then comes in different flavors because I think the time constants matter. And by the way, the ability to get power out, the time constant of draining that matters too. Batteries will play a big role, but once you talk days to years, batteries are simply too capital intensive to make this work. I think the bottom end of that spectrum is undoubtedly done with chemistry. And I would argue there's an enormous advantage of being in liquid fuels, in other words, in hydrocarbons, because they have the energy density, they have the chemical stability, and they're easy to store, easy to move, and easy to transfer back to electricity, albeit at a loss of maybe a factor 2 or so, right? So energy storage on the days to years scale is something they excel at. You can sit on an oil tank for a couple of years, and the cost of having sat on that is actually minimal. And right now, in the current environment, we all wish we would have more oil in storage than we actually do, right? Energy for transportation, and it can apply to cars, trucks, ships, planes, and trains. And you may say, well, cars and automobiles are really out of that. Not really. I like one-on-one comparisons. Assume that fully electric car really works, and somebody comes along and says, I have this tiny little generator, maybe a fuel cell to get political sensitivities right, and it has 30 kilowatts, and I can keep the batteries charged while I go. Suddenly, that car lost a third of its battery, 2/3 of its battery weight, probably a third of its total weight. It has a 1,000-mile, thousands of kilometer range, and it's all around better by having that combination. I think we will likely go back there if we can or need to. Whereas in a city, you can drive entirely on there, and you can optimize the balance between battery and other storage. If you look at low traffic train tracks, you have plenty of those in the US. Electric power in the track or on overhead compared to a diesel electric is just no competition. And then ultimately you can transport energy. Compare transcontinental power lines for renewable power with trucks, trains, barges, oceans, and pipelines. As a rough rule of thumb, if you have a liquid fuel, you are somewhere between 30 and 50 gigajoules per ton. That's about 10,000 kilowatt hours of energy. So at a delivery rate of 1 ton per day, this translates to 400 kilowatt of power, right? A truck coming down a highway once a day delivers 10 megawatts. A train car, about 20 megawatts, and a large freight train, a gigawatt, if it arrives once a day at its destination, right? Trucks coming once an hour, 240 megawatts. Right? On a freeway, you don't even see that. A barge is 600 megawatts if it comes once a day. And ocean tankers carry 100,000 tons, so they're like oil tankers. And a pipeline can run hundreds of gigawatts. It completely overwhelms what an electric power line can do. And a transcontinental electric power line, which gathers photovoltaic energy over large areas and then stands empty 2/3 of the day, is not a good investment. So I would argue for that reason alone, liquids will play a huge role. And we engineers haven't quite figured out yet. We are trying to shoehorn everything in the grid when we really shouldn't. We should figure out how to bypass the long distance grid and make things work more locally. So what's missing for such a picture, right? Cheap photovoltaic power, I would argue, is ready and is spreading fast. Right? Conversion from electricity to chemical energy, think electrolyzers, water splitting of hydrogen to oxygen, but you have other options. That's technically ready, but there's little demand. And I think it's still too expensive for intermittent energy. You need to gain a factor 2 or 3 to make that really work. If you compare, let's say, alkali electrolyzers in Norway, they can run on cheap hydro, but they can't run unless they run 24 hours a day. Conversion to useful liquid fuels with CO2 and hydrogen is close to ready. We know how to do this for 100 years. We can make methanol, dimethyl ether, alkylate fuels, diesel and jet fuel by various means. I think there's little demand for it right now because the oil is sitting there, but it's an established technology, and I would argue, and I'll come to that in a second, it needs downscaling rather than upscaling. I think the least established is carbon dioxide harvesting. Direct air capture extraction from the ocean. That's where I think you have the hardest, the really missing link in this story. Of course, you could start with waste and biomass conversion, which lots of people do, I think it's ready on a small scale. It tends to be messy and make not the right stuff, and it's really limited in scope. So I would set that aside and move to the other ones, or be aggressive here too and convert it all the way to the right fuels. But ultimately, if you want to get the cost down and make all of these pieces really work, you need learning by doing to close the cost gap. Right? And I think you want in every iteration, higher efficiency and lower cost. And one of the big questions one of my students looked into more than a decade ago now was the analysis of economies of scale versus the economies of numbers. It's numbering up versus size. And he made an argument that numbering up has real advantages which were not available 20, 30 years ago. And I think we should really look into that. So if you compare sizing up versus numbering up, chemical engineers think about sizing up, right? And they have the concept of the economies of scale, which basically said that the cost is a function of size, and it's a power law in a simplified version where you simply say it's some power alpha, which tends to be 2/3, right? Numbering up relies on learning rate in manufacturing. It's an empirical observation that if you make the same thing over and over and over again, it gets cheaper. And those folks didn't write down a power law. They said, well, if I double it, I get a factor epsilon, where epsilon could be around 0.8. So then, of course, I can say, well, the nth one is the first one times that epsilon to the log base 2 of that n, because basically for every power of 2, I get a factor epsilon. And it turns out I can integrate that and sum up the cost of all of the ones I built, right? And that then turns out, I put an approximate because I integrated rather than summed. It turns out it is a power law again. And it turns out 1 plus log base 2, if I say that I apologize, I typed that wrong. This should be epsilon because I can convert that. And so I need to fix that, but it's log base 2 of epsilon, and it turns out log base, because epsilon to the log n is the same as n to the log epsilon. And bottom line is that again is roughly 2/3. So, but it's powerful in a different way, that it keeps adding over all applications rather than apply to your single one. And it shows that is sort of reflected in the fact that if you think of an automobile engine, and this is what first triggered me thinking about this, if you look at an automobile engine as a power plant of sorts, it's 100 times cheaper than a conventional power plant. A car engine is about $10 a kilowatt versus $1,000 per kilowatt for a power plant or more. A nuclear power plant can be $7,000, $8,000 a kilowatt. But the bottom line is, if you start thinking about that, you can ask the question, why didn't people build power plants out of granular systems the size of automobile engines and harvest the $10 a kilowatt? Because you cannot afford the personnel cost. But here you see where you didn't need personnel. There's the solar panels. You lay them on the ground and they work. And here you see that we got basically 200 times cheaper between 1975 and 2018 by coming down this power law curve. And in this case, the learning rate is roughly 24%. So it's a remarkable thing. Ask about the poor engineer in 1975. I'm coming back from today and say, I can tell you for a fact of the $1 you spend, 99.5 cents are gone. You explain to me, you tell me what you expect that last half cent you couldn't get rid of is for. They couldn't possibly do that even if they knew what I just told them. So bottom line is, we don't really understand where the learning curve, how it comes about, but it's iteration and iteration. And of course, there has to be a floor. So you should add to that power law here the assumption that there is an irreducible cost, which we need to add, which just doesn't go away. So why have people always thought bigger is better, right? Physics, I would argue, drives to an optimal size. And Eric Dahlgren, when he worked on it as a PhD, looked at many examples. And sometimes bigger is better, and sometimes bigger is not as good. It depends on your specific situation. And I can't help pointing out that if you look at a Fischer-Tropsch process or a Haber-Bosch process, what in the world makes a surface contact catalyst, which needs to shed heat, like to be in a very large tank, right? It really cries out to be smaller. But personnel costs tends to drive you large, because the bigger the mesh, a power plant with a gigawatt doesn't need 100 times as many people as a 10 megawatt unit. So as a result, I would argue, or Eric in his thesis argued, a large driver is cost of personnel. But automation pushes that the other way. And in the 1980s, we couldn't have possibly automated that away. Today we can. And so therefore, how to optimize cost by numbering up or scaling up has changed in the last few years, because we have learned that ability. And there are small systems, they are abundant, and they have dramatic learning. Photovoltaic power is an extreme case with its 24% learning rate. Wind power only got 14 or 15, and I would argue a large fraction of that is because they tried to get big and they didn't get all that big. Right? The automobile internal combustion engine, I already pointed out. If you look at computer-related hardware, you get lots of examples. And appliances, right? Things, your microwave has a little microwave generator, which is dirt cheap. Light bulbs are dirt cheap. The ingredients of your iPhone, your camera, the cost of these things have come down by factors of 100. There are advantages of being small, fast learning and prototyping. You have small items, they have inherently faster learning rate. What you see here from his thesis is Eric's thesis, that the average for large systems is a much lower learning rate than for small things. You also see the caveat. There's a wide spread in both of them. So there's no guarantee that if you pick something and say it's small, it will have fast learning. That's worth keeping in mind. There's less risk in innovation. You can try out a prototype, and if it didn't work, well, you just wasted $10,000. If it turns out you need to build $1 billion plant before you really know that it works, you better be very conservative in your choices. You can also drive modularity in many different ways. You can plug and play. You have compressors. You have all these subsystems, and you scale those down. There are far fewer scale-up issues. If you stay with a scale, the physics doesn't change. If you move from one physical scale to another, the physics tends to change. But automation is now your new bottleneck, because if you make $3 worth of output, I can't have a person watching. You have to deal with every normal operation, and probably quite a few abnormal events need to be automated into your system just as well, because you can't afford hovering over that machine. And of course, there are faster turnaround times, which means the premium for a long lifetime of your equipment just suddenly goes away, which particularly at the beginning is actually important. If you think DAC today can get 10 times better, you don't want an old DAC sitting around from 10 years ago, because it is just too inefficient. So I'm working with a company, and I'm an advisor, even have shares in the company, so not surprisingly, who is trying to close the carbon cycle that way. Eric Dahlgren, who I advised the PhD I just mentioned, actually founded the company, and here with his wife. And here you see his first prototype, which he demonstrated last May. This machine takes CO2 out of the air and converts it into gasoline. So the central theme here is this is mass manufacturing. This thing is aiming for a gallon a day, or if you think in other units, it needs 200 moles of CO2 per day. On a nominal level, at night it wouldn't work because the photovoltaics is not there. So think of that as a nominal rate, just like a kilowatt solar panel only gives it when the sun is shining. It's designed for intermittent photovoltaic power. It uses potassium hydroxide as sorbent. The alkaline electrolysis makes K2C, uses K2CO3, the potassium carbonate, as the electrolyte. That came from the sorbent. It splits it into the water into hydrogen and oxygen, but it also separates the anolyte and catholyte into potassium carbonate and potassium into potassium bicarbonate and potassium hydroxide. The bicarbonate then is further processed to get the CO2 out and turn back to carbonate. It goes back into the electrolysis. But basically, we get our hydroxide back by inside the electrolyzer. We extract the CO2, and in an outgasser, we combine the CO2 and the hydrogen to make methanol. And then we dehydrate the methanol to dimethyl ether and then to gasoline. And then there's a polishing step because the gasoline we make is not yet commercial grade. And at the end of that, we are commercial grade. And here, direct air capture is deeply integrated into the fuel synthesis. We take advantage of the synergies between the two, and the hydrogen production and CO2 concentration share the same overpotential. So we pay the inefficiency once and not twice. And that's what makes this work. But by the same token, we can't really do CO2 as a capture mechanism because we're stuck. So the lessons learned for direct air capture, there's a significant advantage in your energy balance if you need to make fuel, because you store a lot of energy in the fuel. And if you're 50% efficient in this, you're proud of yourself. And you can hide behind that the fact that carbon capture wasn't all that efficient. It greatly simplifies the problem. Blowing air and thermal losses in sorbent generation are dwarfed by chemical energy demand. The kinetics, turns out, is not an issue. It's no better than most DAC, but it's plenty good enough for these things. I would actually argue we sometimes overthink sorbent shots. Low-cost photovoltaic power is absolutely critical to make this work. Energy efficiency is secondary to cost in all of this. Right? We are collecting energy, and we are not all that good at using it, but because it is so cheap, if it's a dedicated solar panel, we are not squeezing the efficiency, we are squeezing the cost. And I would argue generally direct air capture has to learn how to deal with that intermittent power. And we argue that simple is better. Alkali electrolyzers are much more easily managed than fancy high purity demand requirements. And we use off-the-shelf catalysts. There's nothing fancy about our chemical reactions. Yet we made perfect methanol, which was clean, no formaldehyde, no alcohol, no ethanol. It was pure methanol after we squeezed the water out, which of course you have to do. And I would argue inorganic sorbents are environmentally easier, and that becomes quite clear looking at this system. One of the other lessons we learned is that modular mass production lacks off-the-shelf modules. We are coming into a chemical engineering field. The units of operations only exist on the wrong scale. There are lots of things which are not difficult, but nothing is readily available. Compressors, pumps, heating systems, cooling systems, all of that, we have to reinvent the wheels, right? The process design for small scales is actually different, but typically simpler because you have exquisite control over them. You can do things at 1/10 of a degree if you choose so. Low cost in electronics and appliances hints at savings, right? The new challenge are control systems. Everything has to be automated, but it eliminates the challenge of scale up. And computer calculations turn out are cheap. We have one pi can do everything we need. Right? Sensors are often expensive, and we are spending a lot of time thinking about how to make that easier. And I would argue sometimes we want cheaper sensors and more calculations to calibrate. Ultimately, it requires a paradigm shift, which is not just limited to DAC. We can think about this approach to desalination, to power, to all sorts of things. And I think this will create a revolution where the old dinosaurs will stay where they are, but new technologies will go small. I would argue in all of this discussion, and I'm running short on time, I'm afraid, is the DAC is the bottom. And I think we need to get it down to $100 a ton, whereas right now we are more like $1,000. And I would argue $100 is sort of a reasonable number. And one way of looking at it, how much does it hurt the economy if it had to do it overnight by simply applying it? Alternatively, some other technologies will displace it because they happen to be cheaper. But if you take $100 for CO2, that turns out is about $40 per barrel of oil, or somewhere between 4 and 10 cents per kilowatt hour. And on the right, I'm showing you the variance of prices in oil between 1998 and 2023. And I show you the variance in electricity retail prices in the US states. And it turns out they are on that scale. So if you can get to that scale, dealing with a problem is economically manageable. If you put another zero on and say it's $1,000, which is probably closer to where DAC is, then it would ruin the economy. So we have to get from $1,000 to $100. And here now it matters, can you really get there, or is there an irreducible cost that you cannot get rid of? Of course, learning rates now matter too. Right? 20% learning rate implies a 10-fold reduction in cost requires a 1,000-fold increase in cumulative production. That's nothing. We are at kilotons a year, so we end up at megatons a year. Well, megatons a year are not climate relevant. That we are entering the scale of merchant CO2, which is used in industry. And moving from kilotons to megatons is not what does it. On the other hand, if you have 10% learning rate, you are in trouble, and I'll come to that in a second. And I would argue learning rates and irreducible costs depend on technology choices. You can choose well, or you can choose stupidly. If you want to go large, 10% is a good learning rate. If you want to go small, 20% is a decent learning rate. If you insist that you make calcium carbonate in the middle, your energy consumption is set by the calcination of calcium carbonate. There's no way around it. Learning rates are higher for small systems, as I pointed out, and I'm arguing the irreducible costs are likely small, and I give you a little argument flavor of how I think about that. And I would argue land costs are negligible because you can live in a desert, and that cost is not all that much. But let's look at the irreducible cost, whether maybe we could get below $30 a ton. And I look at the energy cost. If you say take the thermodynamic limit, which is, keep in mind, this is an optimistic calculation. It's trying to say how low could it be? That's the irreducible part. $2 a ton. The thermodynamic limit is 22 kilojoules per mole. That's 140 kilowatt hours per ton, or $1.40 at 1 cent a kilowatt hour, where that intermittent solar panel probably lives, right? Sorbent costs, resins can be cheap. The moisture swing material we have, I can purchase for $4 a kilogram in bulk at Alibaba. So if I take, the number is 10 times cheaper than what the National Science, the National Academy suggested would be a nice number. If I now collect over the life of a kilogram of sorbent 1 ton of CO2, that may be 100,000 cycles at 1% loading in about 5 to 10 year lifetime, that would add $4 to the cost of a ton of CO2. The equipment cost I have to wing, right? And I'm arguing it adds about $10 a ton. And I'm saying the sorbent mass for 1 ton of CO2 I can estimate by giving how long a cycle takes and how much I get in a day. And so I need about 3 kilograms of sorbent if I want to collect 1 ton per year. And that in turn, I'm now arguing that I need 3 times the mass of equipment. And I think that's quite conservative. But empirically, we know that cars, appliances, all sorts of things cost around $10 per kilogram if they are mass produced. So taking that number and take 10% annual depreciation, we're talking about $10 per ton of CO2. So adding these numbers up, I'm well below that $30 a ton. So I think the case can be made that the irreducible cost, which I'm not saying we can hit in the next few years, is actually small enough that you can, just like photovoltaic, run down the learning curve without being stopped in the middle. But you do ignore your scaling laws at a risk. I don't want to get into the details of this, but I simply modeled here, if you have demand, and how big is the demand has to be so that you can learn your costs down. And if I give you an irreducible cost of $30 and a learning rate of 20%, which is less than the CO2, then you run up this bottom curve here. And by the time you saturated the voluntary market, you're probably at $100 or less. If, on the other hand, you started with 10% learning rate, chances are you don't make it. Certainly, if your irreducible cost is above $30. So you got to figure out that you can't ignore that. You may not understand it, where it's coming from, but empirically it's there. And if we ignore it at our own risk. And if we follow a 10% learning rate with a technology which uses calcium carbonate, and therefore really can't get below $90 a ton, you're stuck. You will not get the cost down, even if you hypothetically say we hit world emissions. So we got to figure that out. So what do we need to do to DAC to get affordable? I think process engineering is central to improve DAC, which is anathema in the US because all in academic institutions are very weak at process engineering. We need it. That's the central point. Air contacting is not the same as flue gas scrubbing. Passive versus fan-driven designs make a big difference. Multi-stage processes with integrated heat recovery, that I think is where it's going to be. Right now, the thermodynamic requirement is a rounding error in the DAC's energy budget. People often ignore it because it's the heat losses on the way up and down which count. Even with sorbents that are not binding so too strongly, and the heat recovery in thermal cycles is crucial. Sorbents are functioning reasonably well in my view. Small temperature swings and good kinetics are available. What I think remains to be understood is durability, that 100,000 cycles, efficient form factors, and environmental impact. That's where the research on sorbents, in my view, needs to be. We looked at heat recovery in a clever way where we simply said, we have a hot water tank. We take water into a small container, which flashes some of the water into the steam regenerator, which is evacuated. And the rest of the water, which is now colder, is pumped back into your heat reservoir. That pressure jump, because it's liquid water, is small and can be nearly ignored. Then the steam heats the sorbent and slowly CO2 comes off. We gradually, gently pull that out. And as we compress the CO2, we recondense the water at 100 degrees C at 1 atmosphere. And when the CO2 release ceases, we keep sucking on the system to pull all the water out. And if you pull all the water out, we pulled with it all the heat back out. And now we compress that steam back to 1 atmosphere so that it condenses against the heat reservoir we have. And so we basically embedded the entire DAC regenerator into a refrigeration system, into a heat pump, which is driven by water as the working fluid. And in doing so, we can greatly enhance the heat recovery in the system. We can basically get it all back out, except the little bit which we needed to make the CO2 work. I think we need to move to simpler sorbents. We started out with gel-type quaternary ammonium sorbents, which had a moisture swing. One of the things which occurred to me is I think of this as absorption, and I had an endless fight with the chemical engineering community, which always thinks of it as adsorption, but I think it's the water in these interstitial spaces in that gelatinous mess, which is actually where the chemistry happens. One of my students modeled that in great detail. And you can explain everything by saying there's diffusion in that water. And now it's an absorption where there's a scaffolding of resin around it to hold things in place. These resins can be, the water in these resins, title here, can be 40% by weight. So water transport is not in gas-filled pores. The entire transport, the diffusion constants are on the order of 10 to the minus 12 meters squared per second. So Therefore, I can invert that and say I have 20 minutes for things to happen. That implies microns as the typical scale size. Do we really need nanopores at the MOF scale? Or are we much better off to take these gel-type materials where we actually happen to have started? Nanopores get plugged with water, with contaminants. They're mechanically and thermally unstable. You just asked for a whole bunch of problems which you can get around. And I think I would like to go back to where I started on this. We also need to learn how to power DAC with carbon-free intermittent power. We need to take advantage of clean and cheap energy. Renewable energy is clean, but batteries would make it expensive. You can shift your energy regeneration in time if you use cheap sorbents, which are inorganic. And heat and cool offer storage options. Right? We are working on a triple point system where the triple point CO2 stores energy and is cold enough that it actually can take CO2, which is released, and compress it simply by cooling it. And so we are looking at various ways of dealing with that. I think the other big research issue, in my view, is end-of-life considerations, particularly for the sorbents. Small losses are likely and unavoidable. How do we deal with that? Would inorganic sorbents raise less concerns? Keep in mind they are carbonates when they get lost. And how do we deal with decay products like amines and nitrosamines? Right? We need to think about all of that and the impact on water and water quality if we sit out there with tens of thousands of these devices in one place. That can be a water producer or consumer. Neither is ideal. And we need to look at the stability of sorbents. Conclusions. Cheap renewable energy with dispersed, remote, and intermittent operation changes the electric power business completely. Right? Fuel-based electricity is forced to operate intermittently, mirroring renewable power generation. Renewable power should be viewed as raw electricity rather than consumer electricity. And there's a big price differential between the two. And it will be sufficiently low in cost to feed batteries and fuel synthesis. And direct air capture provides the carbon for these fuels. That's how I see this happening. The existing power infrastructure, on the other hand, is ill-equipped for this transition. Nuclear power, thermal coal, natural gas combined cycle plants, they need to operate steadily. Internal combustion engines, aeroderivative turbines, and maybe fuel cells are likely replacements. Long-distance power lines can't afford sitting idle. Transportation of liquid fuels will be advantageous. Batteries round out that picture, but are unlikely to dominate it because of the long-term mismatches. Much of the renewable power in this world does not go directly into the grid. It bypasses the grid until the very end when it's used. It's stored and shipped for later generation of valuable consumer electricity. That's very distinct from cheap raw electricity. And for the transportation sector, it, of course, then feeds in too. You fly airplanes on this stuff. And it allows for very efficient shipping of power. And I would argue DAC plays a crucial role beyond just negative emissions, and climate stabilization, in this view, becomes an afterthought. And I close here, and I thank you for your attention, and I'll be happy to answer questions.
Thank you.
And sorry I ran over.
Thank you very much, Professor Lackner, for this excellent talk. And I'm sure that our audience have got a broad and nice overview about the carbon management and different technologies and what we should do actually in future to get a sustainable economy. The floor is now open for questions. You may write your questions on the chat box on conversation so I can read them. Or maybe you can like raise your hand. Yeah. I
don't know if you can hear me when I speak loud in the room, or is it too far away?
Maybe
I
you can
barely hear you, but with a little help, we'll work it out.
It would be good if you come closer a bit.
I think we have a micro. Maybe we can check it at some point.
I don't know how it works. Okay. Thank you very much for this very nice talk and very refreshing. And it's good to hear a little bit about that, to get optimist again about what can be done and what is the path forward. My main question here would be, what is your view on recent political movements, in the way that it seems that our civilization is not taking the challenge of climate change at the right level. Things are not moving so fast. You mentioned about cost needs to get down, but political will is needed for that. So it feels a little bit, when you hear it at political discussions and the way that the world is evolving, that actually political people, they more think, okay, now the time for change is kind of over. We can try to adapt, but working on mitigation is maybe not the main priority right now. Do you think that what would happen if we go in this way? Is it still something that could be reasonable for us, and that we can say, okay, we could take the action in many years, in some decades, because now it's not the main urgency? What is a little bit your view on that? Because I guess that you've been trying to convince a lot of people around the world about the urgency of that. We are with teams where PhD students are very much committed, engaged, and we feel, okay, there are things to do, but it's not moving that fast. So what would be your view on that? Shall we still keep the hope and try to make things move? I guess so, but with a little bit more experience and distance, what would you say now?
I mean, that's it's the early 90s, when people thought this is crazy, right? Why worry about it, right? I think it's fair to say that in the 90s, climate change was theoretical. We knew from modeling that it will happen. You couldn't really see it over all the natural fluctuation and noise. In 2000, looking carefully, you could see it. In 2010, you didn't need to be careful anymore. You could see it. Now it's starting to be not just visible, it's loud. I think next decade it will really hurt. And so I do think it will happen. It will happen slowly, like everything else. It needs to hurt before people act. The same happened with sewage. I think it's a worthwhile comparison to look back to the 1830s in London with a big stink. And I think it will take some more time, but it's not all that far off, because the effects are getting louder. And I think right now you have other policy issues. I would argue the climate change importance hasn't changed, but we have found new ways to do ourselves in, and which may, in the short term, actually be more dangerous and more critical. I mean, what's going on right now is just frightening, right? And the risk of nuclear war, I think, trumps climate change for now. But I do think eventually we have to solve this problem, and adaptation will help. I would argue on these things I'm discussing here, two things I would observe. One is adaptation only goes so far. The real problem with carbon is it keeps piling up. And therefore, it's never too late to make this happen. The question is how much damage are you willing to tolerate before you turn around, right? But we will turn around because we have no choice. So the other part of this story is that I do think photovoltaic power is changing the game in a way that you could see us very well be independent of oil in the foreseeable future. And that changes the boundary conditions on the problem. On the other hand, I would like to point out that if you look at the US consumption of wood for energy, biomass, wood, right? We are burning wood. We are not thinking of ourselves as a wood-burning society like we were in the 1890s and early 1900s, when wood was the primary energy source in the US still, because it had so much. Our wood consumption for energy has not dropped. It wobbles a little. Right now, it's a little lower than it was in 1900. In 10 years ago, it was a little higher than it was in 1900. As a percentage of the total, it hasn't changed much. So therefore, I think what we are doing here is necessary anyhow, because the Powder River Basin will always have cheap coal. And we will have to balance the book sooner or later. And we may say, well, we are all renewable. What's the big deal? We just still have that 40 gigatons in the background, still chugging along without having changed anything. So I think we need a regulatory framework to make this happen. And I think it will start because it hurts. And yes, unfortunately, it may happen in China before it happens in the US, right? But
Okay.
But it is, you can't ignore physics forever. The laws of nature will assert themselves.
Thank you.
Okay.
I see it. There is also
Yeah, there is one question in the chat box. I'm just reading the question. Thank you for the interesting talk. What scale do you
I just read it. I can read it too. But
yeah, I'm reading it for other
for the audience, yes.
So it would be good for them to hear. So what scale do you expect could be reached if DAC, direct air capture, achieves your optimistic cost projections? You mentioned DAC for energy storage. Do you think it will become the future source of all carbon-based products?
To the extent that it's not biomass, it's quite likely. You can think of it as mining the air for carbon, right? And you want to keep it stable at some reasonable level, maybe 350, right? And I do think we have the capacity at $30 a ton, there would be no question that we would do that. At $100, I think there's a fair likelihood we do it, but now you need the climate premium. At $30, you wouldn't even need that premium. And I do think $100 is doable. 50, I still think is likely. One of the interesting things I didn't say in the talk, if you come down that learning curve, if you grow 1,000-fold from where you are right now, that irreducible cost starts to become visible. Right? Because either it's there or it's not. And in photovoltaics, we have been saying we are about to hit it. We are about to hit it. And we get lower and lower. In the 90s, I put the irreducible cost for photovoltaics where we are right now. And I'm interested to see whether we will fall through that floor or not. But I do think
Is the connection lost?
there's no contradiction. There's a question which says, is it a contradiction to say we recycle the carbon? No, it's not. I think these two things can go side by side. And it's not clear to me which one comes first. Liquid fuels are incredibly powerful. And if done right, they're actually environmentally quite manageable. But you cannot pile up CO2 in the atmosphere. You also shouldn't have NOx and all the other pollutions. So you need to clean up on those just as well. But if you use them in e-fuels in the cycle, you're perfectly fine, right? You are not adding anything. In parallel to that, we have to deal with the fossil fuel we have already emitted and the fossil fuel which we still are likely to emit, right? I can see a transition to a world where we don't need sequestration because we are all synthetic liquid fuels. I can see a world which is living in that intermediate stage for quite some time. And I'm arguing we will find ourselves in there. We have done some simple model calculations where we simply said, let's be really optimistic how fast this thing can be phased in and how fast we can abandon fossil fuels. And if you take that combination, we will touch 500 ppm and then gradually come back down to wherever we want to settle. But we will touch that 500. So I think it is nearly impossible not to do sequestration anymore. In 1980, we could have developed a glide path to 350, which never exceeded it. Right now, we will go to 500, and my guess is that a world with 500 ppm will not be appealing. We will likely try to engineer ourselves out of that problem. How long that will take, I don't know, but I think we will likely end up there. And if we don't immediately start working on it, it's not going to be 500, it's going to be 600 and 700. I used to always say business as usual from here on out to 2100, where will we be? In the 90s, I predicted a little more than 1,000 ppm. Now I'm predicting a little more than 900 ppm if I simply follow the current trajectory, which tells you we have done a little bit, but not much. Right? But a world with 1,000 ppm is a very different world than we live in. And the question is whether we can tolerate that change on a time scale of decades.
Okay.
But
We have
the two things of sequestration and e-fuels can perfectly well live side by side. And to answer your question once more, the 10 years ago or 5 years ago, I would have said the likely starting point is sequestration. Now I wonder whether the likely starting point is not e-fuels. And the current problems make this louder and clearer. You really don't want to depend on a bunch of tankers going through a narrow strait. And if you can distribute the making of fuel to places which you have control over, you would feel a lot better about it. And so I could very well see that e-fuels have other advantages. They have another advantage, that petroleum is far dirtier than an alkylite fuel. And one of the things we learned at Aircela, that for us, it doesn't matter whether we make an alkylite or a conventional gasoline. And burning essentially alkanes is a lot cleaner than burning benzene rings and whatever else is in current gasoline.
okay. I think we have one on the chat box, and then coming to you, Cedric. Okay, thanks for your. The next question is. So the second one also. Okay, I was okay. Then okay.
I'm sorry, I'm reading. And I got ahead of you.
Yes, hello, thanks. Thank you.
Or we go maybe to the computer.
Yeah, it's.
You have too many microphones, huh?
Yes. Yes, good afternoon. At least it's for us, it's the afternoon. I don't know what time it is for you. Thank you for your presentation. I was wondering, to put it metaphorically, in this environmental problems, there's a problem of the overflowing garbage bin, which basically you addressed, and there is the symmetric problem of the empty cupboards, right? So the resources that are going scarce, right? And any economic can be seen as something taking from the cupboards and putting eventually in the garbage bin. And so my question, it seems to me that we talk a lot about the overflowing garbage bin, but very little about the empty cupboards. And my question is this, in your view about this transition between the two worlds, which is desirable, do you see any point where the empty cupboards can be really problematic?
I don't know. I actually got into it from the perspective in the early 90s that the cupboard wasn't as empty as people thought. One of the things which triggered for me to think about it, I ran into and then lost, embarrassingly enough, reprint of the Alaska Geological Survey, casually mentioning that somewhere in northern Alaska are coal seams which hold about 4,000 gigatons of coal. And I said, whoa, we have used at that point maybe 300 gigatons of carbon, and here is a single coal seam this big. Now combine that with the observation that at the time, Sasol had demonstrated that it could make synthetic fuels at about $50 a barrel at prices back then. They were saying if only the price of oil were more than $45 a barrel, we actually would be competitive. It seemed to me that the argument we are running out wasn't so obvious. Then Rogner wrote a paper in 1997, I believe, Rogner et al., which argued there are some 5,000 gigatons available. Then people have demonstrated that we can tap into the methane hydrates under the ocean. The Japanese group has successfully done that. That's worth about probably 10,000 gigatons, at which point the cupboard would be empty because we are running out of oxygen. So from that perspective, I think the running out comes later. We are overfilling the garbage bin, or worse, we ignore the garbage bin, we just dump it in the street, right? And the garbage bin is big enough and the resource base is large enough that this is not going to happen on our watch. But it will eventually happen. And that's why I'm also feel strongly that we need an alternative. And what we are laying out is an alternative which would work, absent of fusion, which at this point is still a pipe dream. And I do think that photovoltaics has, years ago I said there are three big energy sources and we make at least one work. One is solar, one is fossil, and one is nuclear. After Fukushima, nuclear is not doing so well, and it is too expensive, and it has nasty proliferation security issues. Fossil is filthy and dirty and has a really big CO2 problem. And solar at the time was way too intermittent and way too expensive. And now it's just way too intermittent. But the simple idea that it has a levelized cost, which beats the SOx of a gas-fired power plant, makes it completely change the energy infrastructure. In places like where you have explicit competition, you just can't stop them, right? They have a dispatch cost of near zero, and you can build as much as you like because the levelized cost is low enough. They will undercut every gas-fired power plant as long as the sun shines. And the gas-fired power plants now have to deal with the rest of the day. But their costs suddenly jumped up because they can't run 24/7, and they were designed to run 24/7. So the whole system, in the presence of that cheap solar, is unstable and has to find a new equilibrium. And what I'm proposing is there is such an equilibrium, and it involves heavily fuels, provided you can make the direct air capture work. So now I have a motivation to do DAC without worrying about climate. But the climate part, of course, gives you a premium.
Thank you.
And I think without it, I'm afraid coal would be the long-term winner because all the arguments of mass production would apply there too, and you could convert coal to methanol at the source. And I think China is doing that. Let's not kid ourselves.
Okay, can we go to the next question, please? Thank you for the seminar. Your table highlights that absorption and adsorption have high costs and energy needs even at high carbon dioxide concentrations. Given that DSC deals with only 400 ppm, how does the exponentially higher cost of DSC captured carbon dioxide impact the market price and resulting green methanol? Does it remain competitive with fossil-based methanol?
Let me first take issue with the term exponential. From an energy perspective, it's actually logarithmic, which is a huge difference. In other words, if you look at the thermodynamic requirement for a coal plant at 13% going down to 1%, you're talking about 15 kilojoules per mole, or 10, 12, I'm not entirely sure right now, but around there. But if you go from 400 ppm to 200 ppm, because I don't need to scrub the air clean of CO2, I am around 22 kilojoules per mole. So the difference is not all that large. And it turns out most sorbents which are used in coal plants are actually strong enough to take it out of the air. They have usually nasty side effects because they evaporate into the air, but from a simple thermodynamics perspective, they're perfectly fine to do that. The energy requirement is not that much larger, but in practice it is. And Herzog had a very nice way of putting it. He said, assume I have this big bucket full of black little billiard balls, and 1 in 2,500 is red. And he said, I need to move them all out of there and get the red ones. And of course, the more are in there, the more it costs me. And that gets you to Sherwood's law, which basically says the cost of separation is roughly linear. But let me give you another way. These are rolling down an assembly line by you. And I have a machine which only moves forward and grabs whenever there is a red one coming by. Then my cost doesn't change as more flows by. And it turns out thermodynamically, this is not quite correct. And if you dig deep enough into it, the reason is that these molecules don't hold still, and your likelihood of getting the wrong one goes higher as you have more of the wrong one there, and that's where the log term comes from. And but the extra energy you need is actually remarkably small. And it turns out in current designs, the actual thermodynamic requirement is a rounding error on the real energy consumption. You tend to be 10, 20 times more than you need. So we need to learn how to avoid that. And you need to do that more carefully. And I think that's why I'm saying it's a process design issue. It's not a sorbent issue. There are sorbents which have just about the right strength and they have the right kind of kinetics. But we don't have a good method of loading and unloading, which does not waste an awful lot of energy. These thermal swings tend to heat everything up inside, and most of that heat that was just there to warm everything up is lost in the process. We need to get 90+% of that back. And if we don't, it will never be energetically viable. Or we use a process that is not thermally driven.
Okay. Can we go to the next question? It's from Professor Andreas Feening. Thank you for the good overview and sharing your personal view on the options. If we are currently at $1,000 per ton of carbon dioxide and DSC will only work if we have $100 or even $30 per ton of carbon dioxide as unavoidable minimum cost, what if that minimum turns out to be higher? If don't research option other than DSC, if no research options other than DSC, humanity depends on a sort of vague, but at that minimum cost. What is your suggestion on possibly alternative options? that could help if we don't reach sufficiently low cost?
It's a good question. The the answer is you should not place all your bets on one horse. That's the first thing. We need alternatives. However, if I look through the large environment of options, to be honest, the biggest one I see right now is make nuclear and solar work. Right? The problem is we will get stranded at well above 500 ppm, even where we are. I cannot point to an option out there which will avoid it. So I agree with you that we need to look at alternatives. We certainly will have to learn how to adapt. Because we have no choice. And I think there's a real risk that the world comes out empty-handed. And that could really, really hurt. But I don't know how to fix it. I get that this is a risk. I realize there are no guarantees. I'm not saying this is the only bet you should place. I would argue we need to spend a lot of time making nuclear affordable. I think we need to spend a lot of time making point source capture cheaper. We should look at BECCS and everything else. But I think in part, they all suffer from the same thing. In a world where you demand that carbon is cleaned up, we either stop putting it out or we are paying through the nose, or we figure out how to make it cheap. These are your options. And I do think if this is stuck at $500 a ton, there's an awful lot of money to be made to find an alternative. But as a person, I can only do so many things. So that's where my focus is going to be. But nevertheless, I think it's critical that we look at all the other options, including, by the way, solar radiation management, which I think poses enormous risks. But we may not have a choice but to understand it. I've always been an advocate that we need to research it, because I think the argument that we should not research is because then we might do it is backwards. I think it's much more likely that we don't research it, we have a crisis, and then we use it, even though we could have known that it was a really dumb idea. But we don't know because we didn't look. So I do think the reality is we have known that this is a problem since Arrhenius, and who didn't think of it as a problem. He thought of it as an opportunity, but we knew it existed. We have studiously ignored it, and we are still ignoring it, and it will hurt. And I can't point to a silver bullet which says we have another answer which is ready to take over. Should we look for other answers? You bet we need to, because I do think there's a real risk that this doesn't work. If you look at the learning rates, there's no guarantee that you have a 20% learning rate. And unfortunately, nobody understands what makes a good learning rate a good learning rate. We can hand wave, we can come up with all sorts of computer models, but bottom line is, this is uncharted territory, and the world has done this before. Let me put it this way. In 1980, we were convinced that by 2000, we are out of energy. Did we actually solve that problem? Not really, right? We sort of mumbled about it, and maybe the fact that photovoltaic power is so cheap right now is a child of that worry, but it came woefully late to solve the problem. We were convinced at the time. I mean, you can read, but people have to say Albert's peak is going to hit us before 2000, right? And yet we just played along, and in the end, nothing much happened. But this one is the reverse. This problem was about worrying about that the input bucket is empty, and now we don't have a waste bucket, and we know what's going out, and we know that the natural waste bucket is not large enough.
Yeah, I think, yeah.
I can have last question.
Very short, please.
Very short,
We are
very short.
really running out of time. Yeah, please come.
I know
I have an
we're
11 o'clock, which is in 20 minutes from now, so
Just
I'm
over
fine.
really quick question. I mean, you mentioned about the technologies that we have, alternative technologies that we have to look for, but specifically on direct air capture, should we keep learning, or should we keep trying a single opportunity or single alternative to make learning curve more strict, or learning curve so steep? Or should we look for different alternatives to find which technology would have better learning curve? Yeah.
I'm leaning towards the latter. I actually, Habib Azarabadi and I wrote a paper some years ago where we argued the way to do it, is to basically auction direct air capture. And we said at this point, we don't even care what it's for, because we want to get the cost of direct air capture down. If you put it into fizzy drinks, that's fine, because we are not trying to solve the climate problem right now. We are trying to solve the problem of getting the cost down. So we asked hypothetically, if we sell 1,000 ton per year increments and we auction them, which is analogous to what has happened in parts of Europe and South America and the Middle East with solar. You basically say, build me a megawatt photovoltaic unit and I guarantee you a price for electricity. So we argue, build me a direct air capture system that can collect 1,000 tons a year, and we guarantee you the price, which is the lowest bidder in this particular auction. And we argued such a structure would likely get the cost down fastest, but implicit in that is exactly what you said. There are different people with different technologies. I think letting 1,000 flowers bloom is probably smarter than locking into one, because your risk that one doesn't do it is actually quite high. And in a way, that's how these auctions work, right? They don't care how exactly you built your system, but you promise that you can deliver. There are penalties if you don't deliver, but you have a guaranteed price. And some of them will fail because they overpromised and couldn't deliver. But that's the nature of such an auction system, and I think it's better than picking winners. And I think in that world, you can then later extend this and say, any other technology which reduces carbon, it's the price on carbon which ultimately makes it work. And if direct air capture can't get it below $500, then other things will hopefully help. But there's no guarantee that anybody comes below 100 on the necessary scale. There are certainly small players which can do a few tons here and there.
Okay, I think, in terms of time, I think we are a bit ahead. And so, yeah, if there is no further questions, then let's give a big round of applause to our speaker again. And
thank you. I really enjoyed it.
Yeah, it was really a nice discussion and presentation. So before I close today's event, please.
I'm planning to retire, by the way. Maybe I have a little more time to talk about things. And the reason I'm retiring is not that I feel old and decrepit. I mean, I feel old, but not that old. But it's also the current environment at the university is just driven by this new crazy politics is just making it too unpalatable. And I'm fortunately in a situation where I can say I don't need that. So I will have more fun with stuff which is fun rather than fighting bureaucracies and trying to raise money on things.
If you want, there may be some positions opening in Europe, but the funding for research are not so high either.
Yeah, but you are right now ahead of the game.
Yes, I'm saying there may be opening research positions in Europe, but the funding for research here is not that high either. Huh?
Well, I'm too old to relocate, so I might come visit.
Yeah. We shall organize that, yeah, indeed. But okay, many thanks for that, and all the best to this initiative that you have with Eric. Really looking forward to see how it
Yeah, you know
develops.
Eric personally, right? You met Eric.
I think I met him, but just once. But he just left 1 year before I arrived.
Oh, he
So,
left before you arrived. Yeah.
Yes, it was the year before.
As you could see from the picture, he's in downtown Manhattan.
Yep, yeah.
And he's building his machine.
I was checking the website, and we have some ideas. So maybe we will talk about also with one of the researchers in the group who asked you questions. There are also very smart ideas that he's developing on direct air capture systems. So maybe at some point we will get back in touch about it.
Oh, I'll be available.
Okay.
Okay, I think we should now close the event. Before I close today's event, please allow me to thank again Professor Lackner. It's a beautiful talk. And yeah, thank you for accepting our invitation and for your time and delivering this lecture and very nice discussion. I would like to thank to all my colleagues for their help and support. And of course, thanks to all of you who joined today's event and making it a success. We will be announcing the next event of our seminar series within the next few weeks. The advertisement will appear on our department website and our LinkedIn page. So please keep an eye on them. Thank you very much and have a nice weekend to all of you. Thank you very much.
Bye-bye.
Thank you, and thanks for putting up with me for so long.
Oh, it's perfect. No,
It's a pleasure.
Our
Really
pleasure. That's our pleasure. Yeah.
Okay,
Thanks a
take
lot.
care. Bye-bye.
Take care.
Bye-bye.
Take care. Bye-bye.